Hello, everybody. I hope you had a nice Easter weekend, and we are continuing now with the next chapter in our mineralogy class. It is actually not a chapter, it consists only of a few slices, but very important slices about the most important mineral chemical formulas and their exchange vectors. So we have discussed by now all the octaeder spaces and the tetraeder spaces in our silicate minerals, and which elements are sitting on the tetraeder side and which elements are sitting on the octaeder side. And I told you the different mineral species can have also different octaeder sites. That means octaeder sites of different size. So, for example, when we are talking about amphiboles, we have 4 different octaeder spaces. So when the element with the elements with the bigger radii sitting on the larger octaeder spaces, whereas the elements with the smaller radii sitting on the smaller octaeder spaces. Then I showed you also, using the example of the feldspars, that we can have different tetraeder spaces. And you know by now also which elements are sitting on the tetraeder spaces. So now we have a lot of different minerals. Yeah, we have on Earth about 3,000 different minerals, and it would be too much to get from all these 3,000 different minerals their mineral chemical formulas in your head. So nobody is expecting this from you. But for the most common rock-forming minerals, you can use a systematic. So, and with this systematic, you can easily build up the mineral chemical formulas for the most important rock-forming minerals in your igneous and metamorphic rocks. Because otherwise you have always to use books to get the formulas, and that is very time consuming. So now we are going to our next slide, and that is now the method. It's actually a very simple method to write down your formulas. We are starting with the nesosilicates, and you know by now what nesosilicates are. These are silicates where the tetrahedrons are all isolated from each other. So, and therefore we are starting with the most important mineral within the group of the nesosilicates. These are this is the olivine group. So, and the olivine group consists of different end members. I have not written down all the end members. I have only just written down the most important end members. So the olivine group can subdivide it in 2 octaeder spaces, M2 and M1, has 1 tetraeder spaces, and all olivines on this planet have 4 oxygen. So then we have the most prominent end member of the olivine, that is the forsterite. And the forsterite has the mineral chemical formula Mg2SiO4. So when you are writing down the mineral chemical formula, like I'm showing it here, then you can split it in. You are putting 1 magnesium on an M2 side, the other magnesium on the M1 side. So in the M1 and M2 octaeder spaces, they are of different size. So then the silica you are putting on the tetraeder side, and then you have the 4 oxygen. When you like to build up or write down a mineral chemical formula of the olivines, then you must just have a few bridges in your mind. All olivines has 4 oxygen. 1 oxygen is 2 times negative charge, made then 4 multiplied by -2 is -8. So then you have just to balance it with the positive charged electrons. Silica is 4 plus, and of course when we are talking about silicate minerals or the group of the silicate minerals, then there is silica inside. Otherwise these minerals are not called silicates. So, and then you know the forsterite is a magnesium end member, and you are filling up the 2 M spaces with magnesium. Magnesium has 2 electrons in the outermost stream, is 2 times positive charged. Then you have 2 multiplied by 2 for the 2 magnesium. We have 4 plus the 4 silica, and then it is balanced with the 8 minus from the oxygen. So then we can do the next best thing. We are just making an Fm exchange, and the Fm exchange, that is the iron magnesium exchange. We are replacing iron with magnesium in the olivine structure, putting instead of the magnesium on the M1 and the M2 side iron. Then we have the next olivine end member, that is the firelight, and that is the iron bearing olivine, which has the mineral chemical formula Fe2SiO4. So then we can also create a tephroide, and tephroide is a manganese bearing olivine, and manganese has also 2 electrons in the outermost stream, and manganese has nearly the same or is similar to the atomic radius of iron and magnesium. Then we are putting on the M2 and the M1 space manganese. So then we have these 3 end members. So, but when you are doing an olivine analysis on a natural olivine, then you can have a mixture of all these end members. Yeah, you have maybe 70% magnesium inside, 29% iron inside, and 1% manganese inside, something like this. Yeah, and that depends always on the pressure and temperature conditions when this olivine was formed. A high temperature olivine has more magnesium inside, whereas an olivine formed at lower temperature is more iron rich. So that is the Fm exchange, and the Fm exchange can then be used as a good thermometer. So now we are coming to another olivine, and that is the montichelite. And the montichelite is a calcium magnesium bearing olivine with the mineral chemical formula or end member formula CaMgSiO4. So now calcium has a bigger atomic radii compared to the magnesium, the iron, and the manganese. Therefore, we putting then the calcium on the M2 space, whereas the magnesium is remaining on the M1 space. So in this montichelite is very common, or a very common olivine in kimberlites. It is there an indicator for diamond bearing kimberlites. So, and then of course, I mean, I have now not written there, then you can replace in this, or in the montichelite, you can then also do an IFM exchange you are putting then instead of the magnesium iron inside, then you have a calcium iron bearing olivine, and this olivine end member is then called the kirstenite. So, but all olivines, they have 4 oxygen. Now we are coming to the next important group of the nesosilicates, that is the garnet group. The garnet has also an M2 space and an M1 octaeder space. M2 is a little bit bigger than the M1. We have a tetraeder space, and all garnets which you can find on the Earth, on this planet, has 12 oxygen. So I have now written down the 4 most important end members of the garnet group. So therefore we have the pyrope garnet, and the pyrope garnet is a magnesium-rich end member of the garnet with the mineral chemical formula Mg3Al2Si3O12. Let us just check the charge balance. 12 oxygen means we have minus 24 negatives on the oxygen side. Then we must have plus 24 on the cation side. So we have 3 silica, all the garnets on this planet having 3 silica. 3 multiplied by plus 4 is plus 12. Aluminium is 3 times positive charged. 2 multiplied by 3 is 6. And magnesium is 2 times positive charged. 3 multiplied by 2 is 6. Then we have 6 plus 12 is plus 24. And our pyrope garnet is balanced. So then our pyrope garnet is also the high temperature modification of the garnet end members. We are doing the next best thing. We are replacing now magnesium with iron. That means we are doing an FM exchange. That means the only thing which we are changing in our garnet structure is we are replacing iron with magnesium and getting then the iron end member almandine of the garnets, and that is Fe3Al2Si3O12. So, but now we are doing the next best thing. We would like to form a garnet at high or higher pressure conditions. So, and I mean higher pressure conditions are also reflected in the mineral chemistry. Therefore, we are replacing now on the M2 side magnesium and iron with calcium. Calcium has also 2 electrons in the outermost rim. We are dealing then with the garnet end member grossular, which has the mineral chemical formula Ca3Al2Si3O12. So now we are forming a garnet which is stable at low pressure and temperature conditions, and therefore we are replacing, or we are putting our M2 space manganese. So manganese has also 2 electrons in the outermost rim, and the manganese end member of the garnet is called a spessartine with the mineral chemical formula Mn3Al2Si3O12. Going to the next slide, number 3. So now we have just discussed some very important nesosilicates or minerals important minerals from the nesosilicate groups. Then we are going now to another important group which is very dominantly on the felsic side, that means on the continental crust. These are the tectosilicates. I mean, the most common tectosilicate, that is the quartz, which has the mineral chemical formula SiO2. This one I have now not written down here because it is then too simple, but I have written down the feldspar group. So the feldspar group, all of the feldspars having 8 oxygen. Then you have 2 tetraeder places. Yes, I showed you this in class. T1 and T2. So, and within these 2 tetraedrons, you are placing then the big cations like the sodium, the potassium, and the calcium. So, for example, we have the mineral end member albite, which is a plagioclase, but can also be an alkali feldspar, depending on which side of the triangle you are sitting. So the albite is a sodium plagioclase or sodium-bearing alkali feldspar with the mineral chemical formula NaAlSi3O8. I told you all the feldspars having 8 oxygen. That means 8 multiplied by -2 is -16. We have to balance it in front. So then we have 3 silica inside. 3 multiplied by 4 is 12. We have 1 aluminium inside. Aluminium is 3 times positive charge. And we have 1 sodium inside, which is 1 time positive charge. We have then 1 plus 3 plus 12 is 16 times positive, and it's balanced with the 16 times negative from our 8 oxygen. So then we are forming the other plagioclase end member, which is called the anorthite. The anorthite is a calcium-rich plagioclase. So that means we have also 8 oxygen, but we have now to do a balance. Because calcium has, compared to sodium, 2 electrons in the outermost string. So what can we do? We are removing 1 silica, which is 4 times positive. We are just removing 1. And putting instead of the silica a second aluminium inside. So then it is balanced. We have 8 multiplied by -2 is -16. Then 2 multiplied by 4 is +8. +6 from aluminium. We have 14 positive charges, and then the 2 plus from the calcium, 16, and the anorthite is balanced. If you are going to the K-feldspars, which can be subdivided in sanidine, autoclase, and microclean, then we have just to replace potassium with sodium. That means we have potassium, aluminium, Si3O8. So, and these are now the common exchanges in the feldspar group. So now we are going to the next silicate group. These are the inosilicates. So, and the inosilicates can be subdivided in single chain silicates, and single chain silicates are pyroxenes, and then we have double chain silicates, and these are the amphiboles. So the pyroxene group can again subdivided in orthopyroxene and clinopyroxenes. We have done this before in class. So, but now we are coming to the mineral chemical formulas. We are starting with the group of the orthopyroxenes. In general, the pyroxene group has two octaeder spaces, M1 and M2, and two tetraeder spaces, T1 and T2, and has 6 oxygen. All pyroxenes on this planet having 6 oxygen. So then we are making the magnesium end member enstatite. We have Mg2Si2O6. We are having the magnesium sitting on the two octaeder spaces, and we have the 2 silica sitting on the 2 tetraeder spaces and the 6 oxygen. Is this true? 6 multiplied by minus 2 is minus 12. Then we have 2 times 4 plus from the silica is plus 8. And we have the two magnesium, which are together charged 4 times. Then we have plus 4. 4 plus 8 is 12. And then our pyroxene is balanced. We can do then the next best thing. We are replacing magnesium with iron. Then we are making again the Fm exchange, which is then Fe2Si2O6. And the regarding pyroxene is called ferrosilicate. So now we are going to the group of the clinopyroxenes. I have just listed 6 pyroxene. I mean, there are much more pyroxene around on this planet, but I have just written down the most common end member because all of them has 6 oxygen, and it should be actually okay if I'm just showing you these 6 to get a feeling how one is writing down the mineral chemical formula and which elements are sitting on which space depending on the radii of the atoms and the charges. So we have the most common clinopyroxene, that is the diopside. It has the mineral chemical formula CaMgSi2O6. So, and then we can see here as well, the bigger atom calcium is now sitting on the larger octaeder space. Calcium is bigger compared to magnesium. We are doing the next best thing with our diopside. We are making an Fm exchange. So that means we are replacing magnesium on the M1 side with iron. So, and then we are forming the iron end member, and this iron end member is called the Hedenbergite with the mineral chemical formula calcium, iron, Si2O6. So then I have put in this list 2 other important pyroxenes, that is the jadide. So, and there we are replacing on the M2 space calcium with sodium. Jadide is very important in metamorphic petrology because it marks the transition from the green schist into the blue schist, as well as it is very important in the formation of the omphacite when we are going into the eclogite, because The chardeate is formed due to the consuming reaction of albite, and then later on the chardeate will be consumed, or the chardeate component is sitting in the later formed omphacite, which is a typical pyroxene in the eclogate facies. So we have the chardeate, we are putting sodium instead of calcium on the M2 space, and you know sodium has a large ionic radii. So, but now sodium has only one electron in the outermost rim. What are we doing now? We are putting, instead of magnesium or iron aluminium. Aluminium has 3 electrons in the outermost rim. 1 plus 3 is 4, plus the 2 silica is plus 8, and then we have 12 positive charges, and our mineral, the chardeate, is balanced. So now we are going to the acmid, and the acmid is a very important pyroxene when we are talking about igneous rocks. It is very common in silica undersaturated igneous rocks. So the acmid has on the M2 space also an sodium, but we are replacing the aluminium with iron 3+. So that means when we have there iron 3+, then the acmid is also very formed in a very oxidized milieu, yeah? Then we have sodium iron 3+, Si2O6. So then you can do a lot of different other exchanges. You can also replace aluminium and iron 3+ with chromium 3+. Then you are forming, for example, a pyroxene which is called a fuchsite. Yeah. So, and there are a lot of different possibilities. Now we are going to the next slide, and we are going to the inosilicates again, but we are talking now about the double chain. So, and the amphiboles, these are inosilicates with a double chain. So now you know by now a lot of things about, or you have heard about a lot of things of amphiboles. They are very complicated. They are all hydrous minerals, yeah, with an OH2 group. And here, when in the mineral chemical formula from the Charmakite, I have written by mistake OH22. That is wrong. So just remove the 22 and replace it with 2. So they have one OH2 group. Then they have, all of them has 22 oxygen, and they have 8 tetraeder sites. So amphiboles can also be subdivided like the pyroxenes in autoamphiboles and clinoamphiboles, and they are showing a huge variation on exchange vectors. So we are starting now with the structure, yeah? So the amphiboles, they have an A place very at the front, and this A place must not always be occupied, yeah? It is actually only in a few amphibole end members occupied. So, and I have just written down here all in all 11 end members, but if you are going to the literature, you will easily find 50 or 60 amphibole end members because they are showing a huge mineral chemical variety. So you have this A place which is in front, which can host very big atoms, but it is in most cases not occupied. Then we have two M4 spaces, and the M4 spaces are the biggest octaeder spaces. Then we have one M3 space. We have two M2 spaces. The M3 and the M2 spaces are of a medium size, whereas the M4 space is of large size. And then we have two M1 spaces, which are also of smaller size. So then we are starting with the anthophyllite. The anthophyllite is an orthoamphibole with the mineral chemical formula Mg7Si8O22OH2. So let us just check if this is true. Magnesium is 2 times positive charged, then 7 multiplied by 2 is 14. Then we have 8 silica, and all this silica is sitting on the tetraeder sides. 8 multiplied by 4, that is 32. 32 plus 14 is 46. So then we have 22 oxygen. They are 2 times negative charge. That means we have 44. So, and then we have the OH2 group, which gives us another 2 negative charges. And then we have 46 on both sides. And our anthophyllite is balanced. So then we are doing the next best thing. We are doing an FM exchange, and we are replacing some of the magnesium atoms with iron, and the iron has a little bit a smaller atomic radii compared to the magnesium. Therefore, it is sitting here on the smaller spaces. So, and then we are forming a mixture of both. Yeah, you can, when we are talking about olivines or pyroxenes, you can then always form a mixture between forsterite and firelite, or a mixture between enstatite and ferrocylite. So, and here I have just written down a mixture between the magnesium-bearing anthophyllite and the iron-bearing grunerite. That is then the coming tonight. So, if somebody is telling you, I'm coming tonight, then it must not be that this person is coming. It can also be only just a mineralogy student of mine who is studying his or her course material. So now we are going to the next orthoamphibole, as mentioned. That is the grunerite, and that is then the iron 7 Si8 O22 OH2. So then we have the next group, the clinoamphiboles. There we are starting with the tremolite, and we are replacing the magnesium and iron on the M4 places with calcium. Yeah? Calcium in amphiboles is always sitting on the M4 spaces because these spaces are large enough to host calcium. So then we have the tremolite, Ca2, Mg5, Si8, O22, OH2. We are doing the next best thing with the tremolite. We are making an Fm exchange. So then we have still the calcium on the M4 spaces, but we are replacing the magnesium and on the M1, M2 and M3 spaces with iron, and we are forming an actinolite with the mineral chemical formula Ca2, Fi5, Si8, O22, OH2. So now we are forming a hornblende, yeah? And the hornblende has still 2 calcium on the M4 spaces, there's nothing on the M spaces, but we are doing now a Cermak exchange. So, and the Cermak exchange is written down. We are replacing silica plus magnesium with 2 aluminium. So we are putting on the smallest n-octaeder space aluminium. Aluminium is a little bit smaller than magnesium and a little bit bigger than silica, so aluminium can be located on the tetraeder side as well as on the octaeder side. So then we are removing 1 silica, we are removing 1 magnesium and putting 1 aluminium and 1 aluminium in the tetraeder as well as in the octaeder side, and then we have done the Cermak substitution within the hornblende. So, and then we have the mineral chemical formula Ca2, Mg4, Al2, Si7, O22, OH2. And the shortcut for hornblende should actually be HBl. So then we are making a Cermakite, and the Cermakite is called a Cermakite because we are making an 1 Cermak substitution more. So then we have again calcium on the M4 spaces, but we have the magnesium only on M3 and on the M2 spaces, and we are putting additionally on the second M1 space an aluminium. We have now 2 aluminium inside, yeah, and we have 2 aluminium now on the octaeder side, and we are putting another aluminium again on the tetraeder side and removing 1 silica. So then we have the mineral chemical formula Ca2, Mg3, Al4, Si6, O22, OH2. Please remove the 22 on the OH group, there's just 1 OH2. So that is the Cermakite. So in all these exchanges reflecting pressure and temperature conditions while these amphiboles are formed. So now we're coming to the next amphibole, the world famous glaucophan. You know now why the glaucophan is so famous, because it is an index mineral for the blue schist. Glaucophan exists dominantly in blue schist, and that's the amphibole which makes the blue schist blue. So, and therefore we are replacing calcium on the M4 spaces with sodium. So, but now we are having the problem that sodium has only 1 electron in the outermost rim and calcium has 2. So we have to do another balance. So, and we are doing this balance on the M1 spaces where we are putting then 2 aluminium inside. So that means the aluminium, one aluminium is 3 times positive charge and the sodium is only 1 time positive charge. So we have now done the balance to get the beautiful bluish amphibole glaucophan, and you can just go through, write down on every element charges, and then you can see that it is true what I'm telling you here. So now we are doing another thing. We are making the amphibole end member palgasite, and here we have now sodium on the A space. There are also some other amphiboles which have potassium on the A space, yeah. So then the palgasite has sodium on the A space, has 1 electron positive, or is 1 electron positive. On the M4 spaces, it is still hosting 2 calcium, but we have to balance now the aluminium, the sodium, and therefore we are putting an aluminium inside. And then our palgasite is ready. So then we have another clinoamphibole, that is the edenite, and the edenite has also sodium on the A space, but we are doing here only one Charmak. No, we are replacing just aluminium on the tetraeder side to balance the sodium on the A space. So, and when we are going to the palga side, there we have done additionally an Charmak exchange. Therefore, we have to remove 1 silica and 1 magnesium, and we putting then 1 magnesium on the M1 space and having 2 we are removing 1 magnesium on the M1 space and replacing it with 1 aluminium, that is the Charmak substitution, and to balance the sodium, that is the second aluminium in the tetraeder, but you can also do it vice versa. The balance or the charge balance is the same. Whereas the edenite exchange, that is then just sodium balanced with 1 aluminium on the tetraeder side. So, and now last not least in the list of examples which I have handed out to you, we have the Rebekite, and the Rebekite is empty on the A spaces, has 2 sodium on the M4 spaces, and this sodium is then balanced with iron 3 plus on the M1 spaces. So here in these examples I have shown you now also the Charmak substitution, which is silica plus magnesium goes or becoming replaced by 2 aluminium. But of course you can have also an iron Charmak substitution. Then you are replacing 1 silica plus 1 iron with 2 aluminium, or you can have a calcium Charmak substitution. Then you are replacing 1 silica plus calcium with 2 aluminium. So please go through in detail with it, write down the formulas by yourself on a piece of paper and study this, because then you are prepared for the examination. Now we have the last group which I would like to show you here. These are the phyllosilicates and these are the sheet silicates. So in the sheet silicates, that is then just the mica group, and the mica group has an interlayer. You know this by now because I showed you that big bubbles like the potassium, the sodium and the calcium is sitting on in the interlayer, whereas the metals are sitting on the octaeder side, and we can we find in the mica group we have 3 octaeder spaces, we have 2 M2 spaces and 1 M1 space, and we are dealing with 4 tetraeder sites. Phyllosilicates are hydrous minerals as well, having 1 OH2 group, and all phyllosilicates having 10 oxygen, yeah? So I mean the most prominent one from the mica group, yeah? I mean, if you are looking for chloride and serpentine, then they are different. So, but here we are just checking the TOT structure, the sheet silicates with the TOT and TOT structure, or the TOT structure. So then we have the talc. The talc you know by now very well, that is the softest mineral, which has a hardness of 1. So and there, the interlayer space between the two TOT blocks is empty. You can see this in the PowerPoint which I have handed out to you in class, and you can see this of course in the movies which I have uploaded last week. So then we have 3 magnesium sitting on the M2 and M1 spaces. We have 4 silica, we have the 10 oxygen and 1 OH2. We can now do just the balance. We have the 10 oxygen, that means minus 20. Then we have the 4 silica, that is then 4 multiplied by 4 plus, that is plus 16. Then we have the 3 magnesium, that is 22 all in all, together with the with the 2 negative balances from the OH2. We have the minus 22 and our talc is balanced. I will have now just to stop because of the loud music in the background. So now we can continue because the car with the awful loud music is now gone. So now we are talking about, or I will discuss with you, the 3 octaedral micas and afterwards the d-octaedral micas. So we have 3 octaedral micas and these are the group of the biotides. So you know how the biotide looks like. These are black, very thin black sheets. And within these booklets or sheets, you have then the potassium sitting in your interlayer. That is this, yes. So these micas are having then the TOT structure. So therefore the micas have always potassium in the interlayer, but you can have some special micas for or special 3 octaedral biotides or micas, which has then, for example, calcium there. That is a very rare end member, which is then called the clintonide, and that is not called the clintonide after the former US president, because the clintonide was before the president. So then we have here, for example, the phlogopite end member, which has 1 potassium, which is 1 time positive charge, 3 magnesium, which is and every magnesium is 2 times positive charge. We have to make the balance with the potassium on the interlayer. Therefore, we are removing one silica on the tetraeder side and replacing it with one aluminium. Then we can just check if we are getting our 22 positive charge together. We have aluminium plus the 3 silica is aluminium plus the 3 silica, that is 11. No, moment, that is 15. Plus 6 from the magnesium is 21. Plus 1 charge from the potassium is 22. Then it's balanced with the O10 OH2. The next best thing what we can do, we are doing an FM exchange and replacing magnesium with iron. Then we have potassium, Fe3, Si3, Al, O10 OH2. So, but by now we are forming now an istonite, and the istonite has one additionally substitution, and that is, it is making a Charmak exchange. So then we have potassium Mg2Al. We are removing one magnesium on the M1 space, putting there an aluminium inside, and then we are putting another aluminium on the tetraeder side and removing one silica. Then we have the mineral chemical formula: potassium Mg2 Al3 Si2 O10 OH2. So, and then we can do the next best thing, but unfortunately I have not done it when I was constructing the siderophyllite out of the istonite, because there we should do the FM exchange. That means in the siderophyllite we are replacing the magnesium with the iron as well. So please change this now in your document. You are replacing now the Mg2 with Fe2. That means the siderophyllite is then not longer potassium magnesium bearing, it is potassium Fe2 Al Si2 Al2 O10 OH2. So please replace the magnesium with the iron there. So now we are going to the dioctaedral micas. We have the pyrophyllite. So the pyrophyllite has an empty interlayer, and it does not have longer magnesium on the M2 space. We are putting there, instead of the 2 times charged magnesium or iron, we are putting aluminium. So, and that means we have then Al2, because one aluminium has 3 electrons in the outermost ring. The M1 space is then therefore also empty. Yeah? Therefore, the white micas are called dioctaedral, because only the M2 spaces are occupied and the M1 space is empty. So that means we having muscovite, we having the pyrophyllite, that is Al2 Si4 O10 OH2. Then you can just cross-check it if it is balanced. Then we are forming our dioctaedral micas, the muscovite, the paragonite, and the margarite. All these dioctaedral micas having aluminium on the M2 spaces, at least these 3 ones which I'm using as examples, and these are the most common ones. Yeah. So I mean, there are some other varieties around which has then chromium on the M2 space. So then the muscovite has then potassium in the interlayer, then we have potassium, aluminium, 2, and we have now to balance the potassium in the interlayer. Then we have Si3Al on the tetraeder. We are removing one silica and replacing it with one aluminium to balance the one-time positive charged potassium in front. So if we are dehydrating the muscovite, then we will form the regarding K-feldspar, and that is the K-feldspar. So then we can we can replace on the interlayer, we can replace potassium with sodium. Then we are forming the paragonite end member, sodium Al3, Si3, O10, OH2. And if we are dehydrating the paragonite, then we are forming an albite. Whereas when we are hydrating an albite due to retrogression, then we are forming a paragonite, yeah? For example. So then we must have then also a calcium end member, because we have also a plagioclase, which is a calcium-rich end member, and this is called the anorthite. Then we have a calcium-rich deoctaedral mica, which is called then the margarite. So, but now, unfortunately, the margarite has calcium on the interlayer and not sodium and potassium, and that means the calcium is 2 times positive charged, and that means we have to balance it again with an additional aluminium, and therefore we are removing one silica more. We have then only 2 silicas on the tetrahedrons, but 2 aluminiums. So, and then our margarite is balanced. So there are now, I think, 2 or 3 typos within the presentation. I will fix these typos and send then the PDF also to you, but I have mentioned it when we went through. Yeah, for example, the siderophyllite is supposed to be the iron-rich end member of this of the istonite. So, and then there was the amphibole, the hornblende, has a shortcut HBl and not HB, and it has only one OH2 group and not OH22. I will fix this in the PDF and send it around to you, but now you can listen you can watch and listen to the movies. It should not be a problem. So then I have additionally I put here this appendix inside. On this appendix, you have the symbols for the most common rock-forming minerals, and then you can just see the mineral hornblende, yeah? You can go to the mineral hornblende, which is here, and there the shortcut is HBl and not as I have written there HB. I have written the formulas yesterday evening, and then it was already dark here. So then we are having slice number 7, and slice number 7 I have just written you again a list from different minerals and the mineral groups, yeah? There you have a lot of mineral chemical formulas from all the different mineral groups, so that you have something which you can always, or where you can do immediately a checkup. So, and then page number 8, I have some other mineral groups. There we have then also the tectosilicates again, but I put also the carbonates on it, the oxides, the spinel group, the most common hydroxides, some sulfides, sulfates, halides, and the native elements, and some other anions. So that was it for the mineralogy class today. Just look at it and have fun with it, yeah? And I will send you then this evening also around an assignment. That is just a question catalog which you should now easily be able to answer it. And you are handing me the question catalog. You can just hand in next week on Wednesday. Thank you very much.